Hi, my name is Brian Caffo, and this is the lecture on power as part of the Statistical Inference Coursera class. This is part of our Data Science Specialization, and the specialization is co-taught by my co-instructors Jeff Leake and Roger Peng. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. Power is the probability of rejecting the null hypothesis when in fact the null hypothesis is false. So, like its name would suggest, power is a good thing. You want more power. And interestingly, power comes more into play when you fail to reject the null hypothesis than when you reject. And let me try to explain. So imagine if you were to conduct a study that has low power. For example, you want to compare treatment A versus treatment B, and you've only randomized 3 people to receive treatment A and only 3 people to receive treatment B. Then when you make the comparison to see if treatment A results in a better outcome than treatment B, you would not be surprised to get a null result because there were only 3 people in each group. You had very little power to detect a meaningful difference between the groups, so your null result was kind of expected, or kind of what you would think might happen just due to chance alone. On the other hand, if you had 300 people in treatment A and 300 people in treatment B, and you failed to reject, then that would be meaningful because you would expect to see a difference since you collected so much data. And that's why power actually tends to come more into play for null results than it does for non-null results. And the way that power gets used most often is at the time of designing a study. You want to design the study so that you have a reasonable chance of detecting the alternative hypothesis if the alternative hypothesis is true. So let's also cover a couple more details. So a type 2 error is a bad thing, as its name would suggest. An error is failing to reject the null hypothesis when in fact the null hypothesis is false. So the probability of a type 2 error is usually called beta, and power is just 1 minus beta. So the two most meaningful quantities for hypothesis testing in terms of the 2 error rates for hypothesis testing are alpha, the type 1 error rate, and beta, the type 2 error rate. But we tend not to talk so much about beta. Instead, we tend to talk about 1 minus beta, this concept of power. So let's go through a conceptual example, and then we'll go through some specific numerical examples. So remember, we were interested in talking about the hypothesis test for the mean respiratory disturbance index, RDI, in a particular population of obese subjects. So we wanted to test whether mu was 30 versus the alternative that mu was greater than 30. We did a t-statistic, which is, in this case, our sample mean minus the hypothesized value, 30, divided by the standard error of the mean. That statistic, we're assuming, follows a t-distribution under the null hypothesis. So if we calculate the probability that that statistic is bigger than the upper 1 minus alpha quantile of a t-distribution, that probability will be alpha if we calculate it under the null hypothesis when mu is 30. So in this case, then I would write that mu A, in this case, equals 30. Now, power is simply the same calculation, but instead of plugging in mu A equal to 30 for the probability that we're calculating, we plug in mu A for some value greater than 30. That winds up being our power. Now imagine if I were to plug in a mu A of, say, 60, then this will be a large number. And that makes sense, right? Because if we want to detect whether or not the mean for this population is 30 or not, and it's really 60, then we should have a lot of power to detect that, because when we collect our data, there will be values around 60 instead of values around 30. Okay? Now imagine instead if our true alternative mean was 30.00001. Then we wouldn't have a lot of power to detect that because it's quite close to the null value. We're going to have lower power. So this power is a function that depends on the mean under the null hypothesis. If we plug in values close to 30, it's going to look a lot like our type 1 error rate. And if we plug in values way away from 30, it should get bigger and bigger to the point where it's nearly 100% if it's far enough away from 30. Let's assume that our sample mean, x bar, is exactly normally distributed. Whether this is because we're willing to stomach that assumption because we have a large sample size and we're applying the central limit theorem, or if we're willing to just assume that the underlying population is exactly normally distributed. Either way, for the sake of argument, let's assume that x bar is normally distributed and that sigma, the standard deviation of the population, is known. Then we would reject if our z statistic, x bar minus 30 over its standard error, is bigger than z1 minus alpha. This is the same as just saying we're going to reject if x bar is bigger than 30 plus this z quantile times the standard error of the mean. Now notice, under the null hypothesis, x bar follows this distribution: normal with a mean equal to mu naught, in this case 30, and a variance equal to sigma squared over n. Under the alternative, it follows the same distribution. The only difference is instead of mu naught, we have mu a, where mu a is the value under the alternative. So it's very easy to write out in R what our power would be. We want to take p norm of the probability, in other words, the normal probability of getting a sample mean, mu naught plus z times sigma over square root n, or larger, where this probability is simply calculated with mu equal to mu a. So here we have mean equal to mu a. Our standard deviation is the standard error of the mean. And I put lower.tail equals false so that I get the upper probability. Now notice if I were to plug in mu equal to mu naught, then I should get alpha. And now as I plug in, as mu a moves away from alpha, power should get larger and larger. So let's try it. Suppose someone were to give me this information that they wanted to conduct this study. They wanted to test whether or not mu was 30 for this population or it was larger than 30, so mu naught equals 30. They were interested in detecting a difference as large as 32. Their n was 16 that they were hoping to get, and they knew that sigma was around 4. Okay, so here I've plugged in the values: mu naught equals 30, mu a equals 32, sigma equals 4, n equals 16. Here's my z as my normal quantile. And then first I want to show you, if I plug in mu equal to mu naught, that it should give me 5%. So here I plug in mu equal to mu naught and I get 5%. Now I'm plugging in mu equal to mu a, 32, and you see that this jumps up to 64%. So there's a 64% probability of detecting a mean as large as 32 or larger if we conduct this experiment. So here I'm plotting the power curves, which is the power as a function of mu a, as n varies by color here, and as we head to the right on this plot, so as we head along this axis, that's mu a getting bigger, and this axis is power. Okay, so let's take a specific one of these lines and look at it. So this line right here is the power when n equals 8. And what you can see is all of the lines, including this one that we're discussing right now, converge at 0.05 as mu approaches 30. And then what you can see is that power increases as mu a gets larger. Okay, and basically that means we're more likely to detect a difference if the difference we want to detect is very big. And that makes a lot of sense. If something's a huge effect, we should be very probable, it should be very probable to detect it. And then the other thing I would note is that as we head up here, we're seeing sample sizes doubled with each line. I start out with n equal to 8, then I move to n equal to 16 right there, and then 32, and then 64, and then 128. And what you can see is the curves all getting shoved up to higher and higher power earlier and earlier. And this makes a lot of sense as well. In other words, as we collect a lot more data, we should be more likely to detect the power of a specific value of mu a. And so that's why the n equal to 128 curve is uniformly above the n equal to 64 curve, and so on. Let's use RStudio's manipulate function to evaluate power as it relates to the two normal densities. So here I'm going to do library manipulate, then I'm going to define mu naught to be 30. Then I'm going to define a plotting function that depends on the population, standard deviation, the mean under the alternative, the sample size, and the type 1 error rate. Then it does ggplot. So then it's going to execute that plot, but it's going to give me a slider so that I can vary all of these parameters. Let me first describe these two plots before we start using the manipulate function. Currently, the parameters are set at the values we used in the previous calculations. Sigma was 4, mu a was 32, n was 16, and alpha was 5%. So what this plot is saying is, under the null hypothesis, here's the distribution of our sample mean. It's centered at 30, and it has a variance of sigma squared over n. Under the alternative, it's centered at 32, and it has a variance of sigma squared over n. We've set a critical value so that if we get a sample mean that's larger than a specific threshold, we reject the null hypothesis. That's this line. We set this line such that the probability, if the red density is true, the null hypothesis is true, this area, the probability of getting statistics larger than it, is 5%. Now, power is nothing other than the probability of getting larger than this line, which is calibrated to have this area under the red curve is 5%, the probability that we reject if in fact the blue curve is true. That's the power. Here's 1 minus the power, or the type 2 error rate. Okay, now let's start varying things and see what happens. So if we move it so that it's all the way down at 1%, that's just saying that this area right here under the red curve needs to be calibrated to be 1%. As we move it down, let me just reiterate this point. As we move it down, it's going to move to the right like that. But what's going to happen to power? Power is going to go down, right? This area is going down as that thing moves. And what is this saying? By moving alpha down, we're making it harder to reject the null hypothesis. We're making the requirement of having a lot more evidence before we conclude the alternative is true. That simply results in less power. Now it's got a lower type 1 error rate, but a larger type 2 error rate and a lower power. Okay. Conversely, if we increase alpha to the highest level I set here, now we have a 10% type 1 error rate, but we have much better power. In other words, if we are willing to be a little bit looser in when we reject, if we get smaller means and we're still rejecting, then we'll get better power. Of course, we do have a larger type 1 error rate, 10% in this case instead of 5%. So let's set it back to 5%. Let's see what happens as we decrease sigma. Sigma goes all the way down to 1. Okay. Now our black line moves, right? Because these are not standard normal curves. So our rejection region isn't always so many standard errors from the mean. Instead, we've decided to plot this on the scale of the problem. So this black line then depends on sigma. So as we move sigma, the black line moves with it. Okay, so let's move sigma down to the lowest level I'm allowing, which is sigma equal to 1 in this case. Okay, so our black line has moved down and it's still calibrated so that this area is 5%. But what we've seen is we have so little variability in the sample mean that the probability of rejecting, the probability of getting larger than the black line if the blue distribution, alternative distribution, is true, is almost 100%. Okay, what happens if we move in the opposite direction? We make sigma larger. Well, here's sigma very large. Again, we're still calibrated so that this area is 5%, but now power is much lower. And all this is saying is that if we have a lot more noise in our measurements, then we're going to have lower power. Let's try some more. Let's set this back to what it was at for the problem, 4. How about the mean under the alternative? Let's make it bigger. What happens? Well, it just moves along, right? It just moves along to the right, and now we get a lot more power. And the black line doesn't depend on the mean under the alternative, so it doesn't move. And then as it moves towards 30, you can see the power is getting lower, and the lowest the power can be is if it lies right on top of the null distribution, and then the power will be exactly 0.05. Then it'll get a little bit bigger as it moves further away and further away and further away until if we're at 35, we have almost 100% power. Okay, let's set this back to 32, the value that we were using for the problem. How about n? So remember what happens as n increases. Our sample mean gets less variable. More observations go into our sample mean, it gets less variable. So let's see what happens. Okay, less variance in our sample mean, so these densities are getting tighter and tighter. Okay, but the black line moves because remember, it's always got to be calibrated. It's always got to be calibrated so that this area is 5%. But you can see now we have much better power when we have a sample size of 50. If we move it down to a sample size very low, n of 4, again the black line is moved because it has to force this area to be 5%, and now our power is quite low. So I would highly recommend that you go through the code for this manipulate experiment to understand how power works in this particular setting. It's quite easy, but basically what you can see is power has a bunch of knobs, and as you turn them, the power changes in different ways. And in the next slide, we'll summarize the various aspects of power. But using the manipulate function like this, you can actually experiment with it yourself. Briefly here, I give the code for developing this function that you use in manipulate to look at the different aspects of power as you vary sigma, mu a, n, and alpha. So let's just reiterate, when we're testing our alternative being that mu is greater than mu naught, and then I'm going to specify power in terms of 1 minus beta, where beta is the type 2 error rate, then we get this equation. Our power is equal to the probability that x bar is larger than mu naught plus the standard normal quantile times the standard error, where this probability is calculated under the hypothesis that mu equal to mu a. And then I simply reiterate that point here on the next line, where I'm explicitly stating that x bar is normal with mean mu a and variance sigma squared over n. So the point I'd like to make is that the unknowns in this equation are mu a, sigma, n, and beta, or equivalently to beta, the power that you want. The knowns are mu naught, and usually you know alpha. You know exactly which type 1 error rate that you would like. So given these 4 unknowns and our 2 knowns, this is simply an equation. If you specify any 3, you can solve for the 4th. So if you know the alternative mean that you'd like to detect, a sigma that you're willing to assume, the n that you want, then you can solve for power like we've done previously. Otherwise, what you could do is you could say, here's a power that I want, here's a mean that I'd like to detect, and here's a sigma that I can tolerate, and then I'd like to solve for the n that would allow me to have that power, maybe at the process of planning a trial. And this is how power calculations usually work. You are particularly concerned most of the time with either n or beta. You usually either want to figure out, for a particular power that I want, what n would I like to have, or should I have, or I can only conduct a study of this size, of size n. What is my power for doing that? Should I even waste my time? So those are the two most common ways, but of course you could also solve for mu a or sigma. So I'm hoping at this point in the class that you'll be able to take the work we've done for the greater than test and do it for the less than test. H naught mu less than mu naught, just by extending the arguments from the previous set of slides. When you're testing not equal to, just make sure you use the z 1 minus alpha over 2 instead of z 1 minus alpha, that critical value. So for example, for alpha equal to 0.05, you want to make sure you use 1.96 and not 1.645. And then just do the one-sided power for whatever direction mu a is, whether it's mu a greater than mu naught or mu a less than mu naught. And this is only approximately right. It omits a small component of power, but that component of power is only meaningful if mu a and mu naught are close together. So let's go through some basic rules about power. As alpha gets larger, our power gets larger. So the power of a one-sided test is greater than the power of the associated two-sided test, and we can see that by virtue of just dividing alpha by 2 in this bullet point above. The further mu a gets from mu naught, the higher the power is. As n goes up, the sample mean has less variability, and so we have higher power. As sigma goes down, our sample mean has less variability, and so we're going to have higher power. Now here's an interesting fact. Power usually doesn't depend on all of these separate parameters, but on some function of those parameters. And in this particular case, that function is one-dimensional. So you really only need to know one number to calculate power. And it's basically the difference between the null and alternative means divided by the standard error. And power only depends on those things, or if you have power in this number, then you can calculate n. So this quantity, the difference in the means divided by sigma, is called the effect size. And what's nice about the effect size is it's unit free. So when you subtract mu naught and minus mu a and divide it by sigma, you get a unit free quantity, and that's why the effect size is very useful, because being unit free, it has some hope of being interpretable across problems. So we never actually calculate power in the way that I've described in the previous slides. That's for understanding the concepts, and we assumed we knew sigma and the data were either Gaussian or that the sample mean could be believed to be Gaussian because of the central limit theorem. I think for me personally, the most common function I use for calculating power is this function power.t.test in R. So let's just talk a little bit about t-test power before we talk about how you use power.t.test. The argument is very similar to what we did in our normal distribution case. We're going to reject if our test statistic, in this case x bar minus mu naught over the estimated standard error, is now bigger than a t quantile rather than a z quantile, because we're talking about a t-test. Only because we're talking about power, this is going to be calculated not under the hypothesis that mu equal to mu naught, but under the hypothesis that mu equal to mu a, the value under the alternative. It turns out that this statistic, x bar minus mu naught over the standard error, does not follow a t-distribution if the true mean is not mu naught. If it's mu a and mu a is different from mu naught, it doesn't follow a t-distribution. It follows something called the non-central t-distribution, which we're not going to cover. So calculating power requires the ability to evaluate the non-central t-distribution, and that's what power.t.test does for you on your behalf. What's nice about power.t.test is just like before, we have some parameters that we know, mu naught and alpha, and some parameters that we don't know, mu a, sigma, and n, for example. And if you omit one of them but specify the remainder, power.t.test will solve for the one that you've omitted. So let's go through some examples of using power.t.test to either calculate power or calculate sample size or calculate the minimum detectable difference. Okay, let's go through a couple examples, and I'm going to point to this middle one here first. I'm doing power.t.test, so it's calculating t-test power. We're testing h naught, mu equal to mu naught, versus HA, and then the question is whether it's doing a one-sided or two-sided test. Well, in this case, you can see here I've always specified alternate equals one-sided, so that's mu greater than mu naught is what it's testing, or equivalently mu less than mu naught if you appropriately specify the difference in the means as negative. So delta here, this parameter, is the difference in the means. So if I specify n, I specify how different mu a is from mu naught, and I give it a standard deviation of 4. I'm telling it it's a one-sample t-test, and I want one-sided power, and then I'm grabbing the power part of it. Then it gives me my power, 60%. What I show here, you notice in all the other examples I've given here, it also gives 60% as the number. And what I'm showing is that power.t.test, just like the normal power, only depends on the effect size, how different mu naught and mu a are divided by the standard deviation. So here, I specify my delta as 0.5 and give it a standard deviation of 1. And notice, so if I'm defining this numerator as delta, notice this is the same effect size as in this case right here. Okay? And since everything's getting a little clouded, let me re-grab my marker. So delta divided by SD is equivalent between that power.t.test call and this power.t.test call, and that's why they give the same number. The same thing is true here, okay, where it's 100 and 200, and if you divide the two you get 0.5, so it's also true there. Let's go through a couple more examples of using power.t.test. Now in all of these cases I calculated power while inputting n, delta, and the standard deviation. Now, let's try to calculate sample size where I give power.t.test the power that I would like. Okay, so now here, I'm going to again show you in all three cases that it only depends on the effect size. So here, I'm specifying delta of 0.5 and my standard deviation of 1, so an effect size of 0.5 divided by 1, or 0.5, and I'm telling power.t.test I'd like to know what is the relevant sample size if I wanted a power of 80%. Then over here, again I'm doing one sample and one-sided, grabbing n. Okay, and it gives me a sample size of 26, and then in these kinds of calculations you always want to err on the side of conservatism, so you bump it up to 27 whenever you get a fractional value. You always get a fractional value, you always want to bump it up to the nearest integer. So you need a sample of size 27 to have a power of 80% to detect an effect size as large as 0.5. And what I'm showing here is that the calculation is the same as I specify an equivalent effect size of 0.5, whether it's delta of 2 over 4 or delta of 100 over 200, it's always giving me the same number. Now what I'll leave as an exercise for you guys is to, for example, omit delta and put in an n and have power.t.test show you what's the minimum detectable delta in order to have 80% power for a specific sample size. And I think given the code that I've given you here, this shouldn't be too hard of a extension. I would say that I almost always use power.t.test as my first attack on a power calculation. One of the main reasons behind this is that power has a lot, as I think I've maybe explained throughout the lecture, power has kind of a lot of knobs and dials that you can turn, and it's very easy to get tripped up on thinking that you have better power than you have, or thinking that you need a smaller sample size. And so when in doubt, try to make your power calculations as simple as possible. So try to revert the question that you're asking down to a t-test or a binomial test or something like that in order to calculate power as simply as possible. And that will give you maybe a slightly conservative either power or sample size estimate, but on the other hand, you'll be able to understand it quite well. From then, you might want to move on to much more complex power calculations, but as a first pass, you always want to do the t-test power or the normal calculation power or the basic power calculation in a binomial problem as the very first thing that you do.